Hi, welcome to the first of the extra videos after the gathering in Bergen. So one thing I will do is I will finish up this proof that I started on in Bergen, which says that if you have a simply connected Lie algebra, Lie group, and your Lie algebra is the direct product of two other Lie algebras, then your simply connected Lie group is a direct product of some simply connected Lie group itself, which has Lie algebras equal to respectively H1 and H2. So one thing which is important to understand what we're doing in step 2 of the proof. So in step 2 of the proof, we're trying to prove that these subgroups H1 and H2 are also simply connected. And so what we're afraid of is something like this here. So here R2, where I removed 0, is not simply connected because I cannot contract the loop going around it to a point. However, if I'm allowed to go into R3, then I can contract it like this. So here to a point, and then there's no problem. And so what we want then to show is that in the case of the proof in step 2, is that if we have something like this, then we can project it down again to our subspace H1 and get a loop in the smaller space, and that this is well defined. So we consider the proof step 1. We did this earlier. What the trick is then that we look at the projection, like we construct maps from the Lie algebra to itself, which with projects to respectively the x1 and the h1 and the h2 part of the Lie algebra, and then we do then, since the group is simply connected, there is then a corresponding homomorphism of the entire Lie group, which satisfy this property here. We can then take the kernel of the corresponding other map. So here we do H2, phi2, sorry, for H1, and phi1 for H2. And then in order to just make sure that they're connected, we take the identity component so that we're not confused. Then we have the correct Lie algebras. And furthermore, something that I forgot to do when I did it in class, we see that if we have anything that's in that is on this exponential form, then it's e to the phi 1 here, which is in the Lie algebra H, and this is by definition, since H1 is the Lie algebra of large H. We have that this also should be in H1, and similar for the other one. So this maps into H things that are on in the image of the exponential map into H1 and H2. And now, since our definition of simply connected includes connected, and we talked about last time that connected, all elements are a product of exponentials, we get that this phi 1 and phi 2 maps into respectively H1 and H2. And this now that we have these sort of projections to H1 and H2, so we have some group homomorphism going from the large group G into H1 and H2, we're going to use that to show that they're simply connected. And the way we're doing that is essentially this point here, but we have a projection this time. So let gamma be a loop in H1, and then since the large G is simply connected, we know, so I should perhaps put this here. So it's a deformation in G. So we know that in the large space G, we can deform this into a point, and now we need to show that we can do it also in H1. And the way we do it is we apply phi1 to get a curve inside H1, and next we then use that since on exponential elements, this is just the identity, it has to be the identity for the entire, if x is in H1, it has to be the identity in the entire H1 since it's connected. And so this means that this in the image of the curve under phi1 is still gamma of t. So it's the deformation of the same curve to the point phi1 of p. So that means that we have a deformation inside of H1 of the original curve gamma of t to a singular point. And so that means that H1 is simply connected. And similarly, we can do the proof for H2. And then there's one part of the proof that I didn't have time for, and unfortunately I never got back to have that another lecture hour where we need to show that G is a direct product. And here we have then the idea that, okay, if we have these two, if we know that both are simply connected, their product is simply connected, and then we have two simply connected Lie groups with isomorphic Lie algebras, and hence they have to be isomorphic. And if you look at the notes, you can see how you explicitly construct this isomorphism. Okay, that's all we need to do for this proof, so that completes it.